So until this point, if I'm like zooming out, I assume that age was a constant, a complex number, and was of course a complex number 0, 1 random variable. And now I want to make an additional assumption that is, I think, very unnatural, and I want to assume that age itself is complex normal 0, 1, and this guy would be, of course, independent of the noise. But the question is why? You know, assuming that the noise is complex normal, assuming that the noise is Gaussian, this makes a lot of sense, yeah? But now I want to further assume that age itself is complex normal. Why would this make sense? And the answer for this is multipath. And multipath is going to play a very major role in our course. So let's understand why the physics of multipath actually create the complex normal assumption for the channel itself, H. Let's take a look. This is this guy, I think, is very important. So I'm assuming rich multipath. So actually, my impulse response would be reflections with strength beta I and delays tau I. This would be the delays. So if this would be my impulse response. So if I'm interested in the frequency response or the transfer function, of course, this guy would be the Fourier transform of the impulse response. So each one of these deltas would actually freeze the exponential at the place where the delta is approaching 0. So age at carrier Fc would simply be sum beta I, very similar to the impulse response, but now each delta translates into a rotating exponential e to the minus j 2 pi Fc tau I. Okay. So now I want to like portray for you some physical scenario. Let's assume that the delays of this multipath, the fact that actually the signal propagates through multiple paths, are uniform over an interval that is much larger than 1 over Fc. Again, from a slightly different point of view, if we assume that the actual the length of the path is uniform in an interval that is much larger than lambda, yeah, the wavelength of that associated with the carrier frequency, actually we reach the same thing. So consider a situation where, for example, the path length is uniform over, let's say, from 50 meters to 100 meters. Actually, these are the parameters that you will see in the exercise for this lecture. And I'm considering carrier frequency of, let's say, 5 gigahertz. So let's write it down. Let's say that di are uniform from 50 meters to 100 meters. The length of the path. And let's say that I'm working at 5 gigahertz. So that lambda, the wavelength, is actually 6 centimeters. So I think you can agree with me that if the path length is uniform over 50 meters, yeah, like interval, and lambda is only 6 centimeters, then essentially this guy, the phase can be uniform, can be assumed very easily uniform 0 to pi, because the interval on which the length is uniform is much larger than the wavelength that we're considering. So the transfer function evaluated at Fc would be sum beta I. These guys are our strength, and these guys phi I assume are uniform 0 to pi and IID. Okay, makes sense. Let's say for this situation where the path length is uniform over a relatively large interval makes a lot of sense. So the real part of HFC would be some beta I, and the real part of the exponential would be cosine phi I. The imaginary part of HFC would be minus, because imaginary part of e to the minus j phi I is minus sine phi I. So minus some I, beta I, sine phi I. Excellent. And now to the key observation, to the key point, maybe the basis, the engine of everything. If we assume that we are in rich multipath, meaning that there are a lot of reflections, so the CLT, the central limit theorem, says that the real part of HFC would tend to be normal with zero mean, because the mean of each guy here is 0, and some variance sigma square. In our case, sigma square would simply be half of the sum of beta I square. The same way, using the same consideration, again, this is like the key to everything. Using the same consideration, the imaginary part of H valued on FC would tend to be normal with 0 and sigma square. So each one of my components is now normal 0 sigma square. In order to make sure that we have like a complex normal random variable for HFC, we need to prove another thing, and the other thing is that these guys are independent. But of course, if I'm taking a look at the expectation, of real HFC, multiplied by in HFC, due to the fact that my phi i's are IID, so all the cross terms would immediately be annihilated, and taking also into consideration that the integral over 0 to pi of sine 2 theta is 0, then essentially what I have that this guy is 0. So again, to summarize, the real part of HFC, the transfer function evaluated on the carrier frequency FC, is normal 0 sigma square. The imaginary part is normal 0 sigma square, and these guys are uncorrelated, so Gaussian and uncorrelated IID. So this means actually that HFC itself is complex normal 0 to sigma square. Again, to wrap this thing up, again, very, very important, the physical interpretation or the physical reasoning for the assumption that the channel itself is complex normal is multipath. So I assume multipath, and again, the engine of my proof is the central limit theorem, the CLT. I assume multipath, then the transfer function itself tends to be complex normal 0 to sigma square, or of course I can normalize to complex normal 0, 1, and then play with the intensity of the noise to have the average SNR that I want. Very, very important point. Very, very important point. Okay.